Integration by parts is sometimes required for word problems. In this case, we have a rocket accelerating by burning its onboard fuel so its mass decreases with time. We suppose the initial mass of the rocket at liftoff, including its fuel, is m, the fuel is consumed at the rate r, and the exhaust gases are ejected with a constant velocity of ve relative to the rocket. A model for the velocity of the rocket at time t is given by the equation v at t is equal to negative gt minus ve ln of m minus rt over m, where g is the acceleration due to gravity and t is not too large. If g is equal to 9.8 meters per second squared, m is equal to 30,000 kilograms, r is equal to 160 kilograms per second, and ve is equal to 3,000 meters per second, we must find the height of the rocket 1 minute after liftoff. To start off solving this problem, we're going to set up our known and unknown variables. So we know that since we have a function of velocity, the area under the graph of velocity is equal to the height, which is what we're trying to find. So in this case, height is our unknown. We also know what the values of g, m, r, and ve are since they're given in the problem. Additionally, we know that we want to find the height of the rocket 1 minute after liftoff, which is a period between 0 and 60 seconds. So basically, the integral that we're going to set up is that height at time t is equal to the integral from 0 to 60 of negative gt minus ve ln m minus rt over m. The fourth property listed in of the definite integral listed in the James Stewart 7th edition Calculus Early Transcendentals textbook states that, let's get this written down, an integral, a definite integral with an upper boundary of b and a lower boundary of a of f at x minus g at x dx is equal to and this property basically allows us to split the following integral, which has one part that we know how to derive simply already, and another one that's a little more complicated because it has ln, into two parts, so that we can solve the easier one first. So this would give us, if we were to split up this as f at x and this as g at x, then we would get the derivative of, from 0 to 60, the antiderivative, of negative g at t, so we're going to take the negative and put it outside since it's a constant, minus, and we're going to take ve and take it outside because it's constant right here. We're going to take it outside from 0 to 60 of ln m minus rt over m. And now that we've done this, we can actually look back at it and see that the first integral that we have is actually quite simple to solve. So we could take this right here, and we know that it would become negative g over g divided by 2 t squared from 0 to 60. And there we already have a part of our word problem solved. And now we have to take a look at our second integral over here, and we're going to have to solve this one. So to do this one, and to make it a little easier, we're going to use substitution and let x, just any variable, equal to m minus rt over m. So that means that when we derive x, dx is equal to negative r over m of dt. So when t equals 60, which is the upper boundary, x is going to equal something else, because of course when we use substitution, we have to change our upper and lower boundaries accordingly. And when t equals 0, x is going to equal something else. And in order to figure out exactly what that is, we're going to use these values that we've been given earlier. So we know that since x is equal to m minus rt over m, we can just go ahead and sub it in to figure out what x will equal to when t is 60. So in this case, we have 30,000 minus r is 160. And here we're setting up t as 60, so it's going to be divided by 30,000 kilograms. So in this case, when t equals 60, x is going to equal to 0.68. So here we've created our new upper boundary. That's going to go right here. So when, let's take for instance, we're going to go ahead and just put in our other boundary, so in this case 0. When this is equal to 0, this entire thing gets crossed out, 30,000 over 30,000, x is equal to 1. So this is going to be our new lower boundary. And now that we're done with this, we can just move it out of the way and free up some extra space. Boundaries set up, we're going to write down our new integral that we've created, so our modified integral. So in this case, I'm just going to take out all of the constants that we have, so we're going to have mve over r, so all our constants are in front, and this is actually negative because it's minus in the other case. So our lower boundary over here is 1, and our upper boundary is 0.68. So this is going to be now ln x dx. So in this case, we're going to have to use integration by parts to figure out how to solve for ln x dx. So in this case, we're going to assume that ln x dx is actually 1 ln x dx. Okay, so now that we know that we have to set up a u and a v, so we're going to let u equal to ln x, and u prime therefore will equal to 1 over x dx. And as a quick recap, we just set up ln x as u because we don't know how to do the antiderivative of ln x, but we are aware of how to do the derivative of ln x. And that would of course make our v prime equal to 1 dx, and our v therefore equal to x. And I just did the antiderivative of a 1. So following the format, this would make our integral from 1 to 0.68 of ln x dx equal to, here we're going to take u and bring it to v, so that will be x ln x minus integral of, and here we're going to take u prime and bring it to v, so this is going to be x 1 over x dx, and this is going to equal to x times 1 over x is just equal to x over x, so this whole thing is just equal to 1. So this is going to be x ln x minus antiderivative of 1, which is x, so this is x ln x minus x plus c, and there is your integration by parts of m of v over r, because you remember we took this out as it was a constant, it was in front before, so this is x ln x minus x inside, and it is from 1 to 0.68. And if we go up and look over here at what we had before, so this part right here I'm looking at, we're just going to take this and rewrite it over down here. So what we're going to end up with is our total equation is equal to negative g over 2t squared from 0 to 60 minus mve over r of x ln x minus x from 1 to 0.68. Okay, so the last part here that we have is just plugging in the values and getting a final answer for our height. and that's a little more tedious. So basically for this, we're using the fundamental theorem of calculus, and we just know that it's going to be 1/2 of g at 60 squared minus 0, because when you plug in 0, it's going to be 0. So it's just equal to 1/2 g 9.8 meters per second squared times 3,600 seconds squared, and that's just because I squared 60, and we're going to get a total of negative, because there's a negative up here, we're going to get a total of negative 17,640 meters. And so, taking a look at the original question we were posed, find the height of the rocket 1 minute after liftoff, we can now conclude by saying, therefore, the height of the rocket 1 minute after liftoff is approximately 14,844 meters.